Okay, so we're going to start with problem number 17. And let me just pause it here for a second. Okay, so we're on problem number 17. And this is what's called a statics problem because there's nothing moving. And so let's just draw a picture of what's going on. So we have this rope, another rope. We have a wall. We have another, like a ceiling. Let's move these over so they're connected. So we'll show them as being stationary by drawing these little dashed lines. And then we have another cable that's going downward to the person. And I'm just going to represent the person as a square, like that. So these are all ropes. So ropes, they're going to be in tension, which means that there's going to be a stretch to them. We know this angle is 37 degrees. And let's see, the weight or the mass of this individual, let's call this M, is equal to actually the weight. So his weight, which is due to the mass of the body, is 600 newtons. And so we're going to have a tension in this cable, we'll call this T1. We're going to have tension in this cable, T2. And so nothing's moving. So what happens is there's two equilibrium equations. There's the sum of the forces in the x direction equals 0, where we're going to define our coordinate system as such. So there's the x direction, there's the y direction. We'll define positive x in the right direction, positive y in the vertical direction. So we are going to say the sum of the forces in the x direction at this point are equal to 0, and some of the forces in the y direction are equal to 0, because if they weren't 0, then we have some movement. But in equilibrium, this is what's called equilibrium. Is the case where nothing's moving. Okay, so what we do is we draw a free body diagram around this point, and that shows all the forces that are acting on that point. So we're going to have three forces. We're going to have the force that's pulling in this direction, and a force pulling horizontally in that direction, and we're going to have a force pulling downward in that direction. And we know some geometry. We know that the angle here is 37 degrees. So we also know, because these are two parallel lines, that this also is 37 degrees. And when we have a force that's not either horizontal or vertical, but it's some angle, we break it up into two components. We break it up into a horizontal component and a vertical component. These are vectors to represent the force, and the force has both magnitude and direction, but the force can always be broken up into an x component and a y component. So we're going to call this T2, which is the tension in that cable. We'll call this T1, and we'll call this W, the weight, which is equal to 600 newtons. And then these component forces are going to be T1y and T1x. Now once you've broken up all the forces that are not either in the x or y direction into their components, then we can then write the sum of the forces in the x direction and the sum of the forces in the y direction. So the sum of the forces in the x direction is 0. So what do we have? We have this force and that force, the components. T2 is in the negative direction, so we put a negative sign because it's going this direction, whereas positive x direction is there. And then T1x is going to be in this direction. That equals 0. Okay, so that's the sum of the forces in the x direction. Some of the forces in the y direction are also equal to 0. So let's see what we have. We have this force pushing down and this force pulling up to balance it. So in the positive y direction, we have T1y, and in the negative y direction, we have W. So from the second equation, we can solve for T1 sub y, T1y. That's going to be equal to W. And W is 600 newtons. So that's this component of one of the unknown forces. Now, through geometry, we can relate this force to that force, because there's a couple of ways of doing it. We can solve. Well, we know this, and we know the angle, so we can calculate Tx. So, for example, it's a right triangle, so the tangent of theta, which theta is 37 degrees, is equal to the length of the opposite side divided by the adjacent side. So we know T sub 1y from the sum of the forces in the y direction. So we can solve for T1x is going to be equal to T1y divided by the tangent of 37 degrees. T1y was 600 newtons, tangent of 37 degrees. And let's get my calculator out. So make sure you're in degrees, calculator in degrees. So we have 600 divided by the tangent, 37 degrees, 796 newtons. Okay, so anyway, we had a little delay there while I figured out something for the math class. Anyway, let's see what the question was. Find the tension in each cable supporting the 600 Newton cat. Okay, so anyway, we figured out the vertical force, and that was T1y, which is 600 newtons. So that's this vector here. We figured out this from geometry, 796 newtons. So the tension in cable T2 is just equal to, from here, we know that T2 is equal to T1x. We solve for it. So tension T2 is 796 newtons. And then finally, to find T1, we have to take the Pythagorean theorem to find the resulting tension. So we do T1x squared plus T1y squared. Those are the two sides of the right triangle. And so the length of the hypotenuse, which is also the resultant force, is just the square root of the square. So we take 796 squared plus 600 squared, and we take the square root of that, and we get 997 newtons. So if we go back to our original picture here, we know that T2 is equal to T1x, which is 796. This cable is just going to be 600 newtons, 0 newtons. And then this one is 997. 997 newtons. So let's stop and just check the answer. Okay, so I checked the answers. That's correct. So suppose the horizontal cable were reattached higher up the wall. With the tension in the other cable increase, decrease, or stay the same. So what they're saying is, if we took this and and pulled it up there, what would happen? So let's add a page in here just so we can look at the original drawing. So what would happen is we would have, if we drew this free body diagram, we'd have, say, that going in that direction, and that going in that direction, and that going down like that. And this still would be 37 degrees between these two. So let's see what happens if we draw our x component and our y component. And we have our x component and our y component here. So this would be T1y, T1x, T2x, T2y. So what would happen, and this would be 600 newtons, because we have this y component of that. Let's do the sum of the forces in the y direction. But you're going to have to equal 0. It's an equilibrium. So we have T2y plus T1y minus 600. So if we had this term here, then this is going to be some positive value. So this is going to be less. It's going to be smaller. And since this is smaller, then this one is smaller as well, because we have the same angle, so they have to have similar triangles. So this one would just be smaller, and then when we do the sum of the forces in the x direction, then since this is smaller and that's smaller, then this length would be less. So what's the question? The tension in the other cable increase, decrease, what's going to decrease? Because this is going to be less, it's going to be less, so the sum of the two vectors is going to be less. So the answer would be that T1 is going to be less than whatever the original amount was, which was 997 newtons. So let's just check to see what it says here in the solution manual. So I'm going to switch over here so you can see what they say. Hopefully I'm right. So it says, if the left end of the original horizontal cable was attached to a point higher up the wall, the tension in this cable would then have an upward component. So we said this upward component would support part of the weight of the cat vertical, thus decreasing the tension in the cable on the right. So that's exactly what we just said. So we're good. So now we're on problem number 20, which is, again, another equilibrium problem. It's equilibrium because nothing's moving. And we look at the drawing and we read the problem. So it says the leg and cast in figure 420 weigh 220 newtons. Determine the weight W2 and the angle alpha needed so that no force is exerted on the hip joint by the leg put in the cast. So let's draw a picture, see what's going on here. So we have this weight that's pulling up, and we have this other support, which is W2, and some angle alpha, and then we have the weight coming down like this, straight down. So that's what's happening like this. And as far as the geometry is concerned, let's draw some horizontal lines so we can define these angles. So this angle is 40 degrees. This angle is unknown. This weight, W1, is equal to 220 newtons. Let's call this T1 and T2. They'll both be in tension. They'll both be ropes. And we know that T2 is equal to 110 newtons because there's a weight that goes over this pulley and it pulls down. And so the tension has to go, it goes straight through and has to equal it. Okay. So what we end up with is we end up with components of the two tensions. We have an X component and a Y component to give us the sum and we have an x component here and a y component. Apparently I've drawn this not quite right. Okay, so there it is. So we're going to call this, let's use red, this would be T1y, T1x, T2x, T2y. And we're going to look at the forces around this point. So again, because it's in equilibrium, we know that the sum of the forces in the x equals 0. And the sum of the forces in the x direction are, we have T2x, which is pointing in the negative direction, and we have T1x, which is pointing in the positive direction. So those are the only two x forces. And then we have the sum of the forces in the y direction, and we have three. We have these two vertical forces and this one down. So we have down there. So we have T2y, which is going up. We have T1y, which is also going up. And we have 220 newtons, which is going down. We also know that we can relate these two, or we can relate T2 to either one of these. So we know that T2x, which is this force, if we do the geometry, this is the adjacent side and this is the hypotenuse, so we use the cosine. So we know the cosine, I'm going to write it slow here, cosine 40 degrees is equal to T2x over T2. So if we solve for T2x, it's going to be T2 times the cosine of 40 degrees. Likewise, the sine of 40 degrees is equal to T2y over T2. And from that we get that T2y is equal to T2 times the sine of 40 degrees. So let's go ahead and calculate those. 110 times the cosine of 40 degrees is equal to, and 110 times the sine of 40 degrees is equal. So let's get our calculator out. 110 times the cosine of 40 degrees is 84.3 newtons. And 110 times the sine of 40 degrees is 70.7. Okay, so those are these two. So from this equation, we can solve for T1x is just equal to T2x, which is equal to, right there, 84.3. And then we can solve this one for T1y. It's going to be equal to 220 minus T2y. So T1y is equal to 220 newtons minus T2y, which we calculated down there to be 70.7 newtons. So we have 220 minus 70.7, 149.3. Okay, so now we have the two legs of this triangle, and then to find the tension, we can find the tension as well as finding the angle. So it says determine the weight W2, which is the same as the tension in this wire, and the angle. So T2, using the Pythagorean theorem, is actually T1, sorry. So T1 is equal to T1x squared plus T2x squared. T1, I don't know why I said that. T1y, because they're the two sides of a right triangle. Here's a right angle. So it's Pythagorean theorem. So T1 is equal to the square root. T1x is 84.3 newtons. T1y is 149.3. I probably carried one additional, too many possibly significant figures. Don't worry about that right now. Okay, so the newtons are going to, when you take the square root of newton squared, you'll get newtons. So we just do the numbers. 84.3 squared plus 149.3 0.3 squared. Take the square root, I raise it to the 0.5 power. I get T1 is 171 newtons. So that's the weight, and that's what the tension needs to be. And then the angle, alpha, we can use any one of the trig functions because we have all the sides of the triangle. So the sides of the triangles are 149.3, 84.3, and 171. So, and this is the angle alpha, so we can use the tangent. So the alpha is going to be the inverse tangent of the opposite over the adjacent, which is 84.3. So alpha is equal to, so we do the inverse tangent of 149.3 divided by 84.3, 60.5 degrees. Okay, so let's stop here and check it out. Okay, so those are the correct answers. I rounded off a little bit to one less significant figure, but the procedure is correct. So again, what we did was we drew this sketch with the two tensions in the cables and the weight. We knew the weight. We also knew the tension in this wire, this cable. Because we knew the tension and the angles, we could just use geometry to find these two values. Then to find these unknowns, we did the sum of the forces in the x direction, which were this is in the negative and this is in the positive, and that had to equal 0. In the vertical direction, we had this, which is positive, this, which is positive going up, this, which is negative going down. So once we found T2x from geometry and this known force, we solved for T1x, which was on the other side, I think. T1x is equal to T2x, and then we could solve for T1y from the sum of the forces in the y direction because we had also calculated T2y, which is down here for geometry. That gave us T1y, which is this force. And we used the Pythagorean theorem for this right triangle to find T1, and then we used the fact that we knew all three sides of the triangle. I chose to use the tangent because that's opposite or adjacent, but it would just have been easy to use the sine or the cosine, depending on which one you want to use, and you would still end up with, you would use, if it was a sine, you'd use the inverse sine of this divided by that. If it's a cosine, we'd do the inverse cosine of this divided by that, and then every time you get 60.5 degrees. Okay, we're on number 25. So we have a 5-kilogram bucket of water is raised from a well by a rope. If the upward acceleration of the bucket is 3 meters per second squared, find the force exerted by the rope on the bucket. So let's represent that is the bucket, and we have a rope that's attached to it. And the mass of the bucket, so let's say mass is equal to 5.0 kilograms. And the acceleration of the bucket is 3.0 meters per second squared. Let's define a positive coordinate system here. So we're going to define positive y in that direction, which agrees with our acceleration because the acceleration is in the same direction as positive y. And then we have the tension there. And we're only dealing with the y direction, so we don't have to deal with the x direction. There's nothing happening there. There are no forces. So we do the sum of the forces in the y direction. Because it's moving, it's not equal to 0. It's equal to the mass times the acceleration. And the forces that we have acting on this, we have two forces. We have the weight of the bucket. So that's the weight. And we have the tension. So the tension is positive, and the weight is negative because the tension is being pulled up and the weight is pulling down. So that's how you get the signs correct. Okay, now the weight of any object is just equal to its mass times acceleration due to gravity. So the weight is going to be equal to 5 kilograms times g, which is 9.8 meters per second squared. And it's not negative because g is always positive. A could be negative, but g is always positive. Weight is always positive. And then we reflect which way the weight's going based upon how we define positive y, and that's pretty much it. Okay, so 5 times 9.8 is 49. So the weight of the bucket is 49 newtons. The mass is 5 kilograms. So we can now solve for T from the sum of the forces. Solve for T. So T is equal to the mass times the acceleration plus the weight. Now the weight's always positive. We have a negative sign here because it's going the opposite direction of positive y. And the acceleration in this case is positive, so these actually are positive plus positive. So the tension in the bucket is higher than the weight of the bucket. And now if you had a real weak rope and you're just holding the bucket, everything's fine. But if you jerked up the bucket, then that acceleration, as you jerk it, as the bucket's trying to move, would add additional tension into the rope and cause it to break. So if you have if you're not sure about the strength of your rope, then you want to do things nice and smoothly. And that's kind of the idea with fishing line. You know, if you have, say, if your strength of your fishing line is less than the weight of the fish that you're trying to catch, for one thing, a fish isn't going to weigh as much in the water as it does in the air, for one thing. But if you caught the fish and you jerk too quickly, then you might exceed the strength. So that's why you have to do it very gently, and it's much more skillful if the test of the wire is test of the line is lower. Okay, so let's just plug in the numbers here. Tension is equal to mass, which is 5 kilograms, times the acceleration, which is 3.0 meters per second squared, plus the weight, which is 49 newtons. Kilogram meters per second squared is a newton, so we get 15 newtons plus, and we probably only have 2 significant figures here, so let's take that out of there. 15 newtons plus 49 newtons, and that's equal to 64 newtons. So that's the tension in the rope, which is also the force exerted by the rope on the bucket. So let me just pause for a second, check the answer. Okay, so that's it. That's the correct answer. So we're now on problem number 28. So what we have is a triangle. Let's draw a triangular situation. And so there's a triangle. And we have a pulley where we have 2 weights involved. We have a weight that's dangling. And we have a weight here, or mass, that's parallel to the surface. And we are going to assume that there's no friction associated with this one. So let's draw a circle here as the pulley, and let's draw the tension down here. This is a frictionless pulley, which means it doesn't contribute anything except just transfers the force. So we're going to call this T, and the tension in this rope has to equal the tension in that rope when this is frictionless. This is going to have a mass, we'll call this M1, 10 kilograms, and this will have a mass M2 equal to 5 kilograms. And these will both be they'll have an associated weight with them. This will have a weight W1, and this will have a weight W2, which will be in the downward direction. So this is going to be weight 1, and this will be weight 2. Okay, so we have 2 packing crates of mass 10 kilograms and 5 kilograms connected by a light string, which means it has no mass, that passes over a frictionless pulley, which means this tension is going to be the same. The 5 kilogram crate lies in a smooth incline. Smooth means no friction, of 40 degrees. So this is 40 degrees. Find the acceleration of the 5 kilogram crate and the tension in the string. It turns out the acceleration of the 5 kilogram crate will be the same as the 10 kilogram crate, at least in terms of magnitude, because they're hooked together, so they have to match up. Okay, so this is one of these two-body situations, and so we do a diagram of each one. So we're going to look at the 10 kilogram crate here, and we'll look at the 5 kilogram crate here. We're going to rotate this so it's a particular angle. So we have a tension pulling in this direction called T. We also have a same tension pulling in this direction. And so it's also T. We have the 2 weights. We have this weight, and we have this weight. W1, W2. And what we're going to do is we're going to define positive Y in this direction for this particular diagram. And we're going to call positive Y in this direction and positive X in this direction. And it's completely arbitrary, it doesn't really matter, but we're but the problem is that this one is in the Y direction. This force is actually somewhere in the X and Y direction. So we're going to break this force up into 2 parts. We're going to have a Y direction part, and we're going to have an X direction part based on this definition. So this will be Y, W2Y, and this side will be W2X, and this will be W2. So let's go ahead and do that out of the way. And let's see, what's the angle of this thing? Well, this angle is, this is the hard part, to keep all this straight. So that's 40 degrees. So is this 40 degrees or is that 40 degrees? The question. Well, one way you can do it is you can think about it as this thing tips over. This angle here should go to 0, and therefore one of these angles should go to 0. And the one that's going to go to 0 is this one here. So we can kind of infer that this is 40 degrees. That would be a way to infer it. You could also just use parallel line. You could look at these 2 lines parallel. This line's perpendicular to that line, and so forth and so on. So there are other ways of doing it, but so whichever one you feel comfortable with. So what we can say is W2X is equal to what? Well, here's the angle. This is the adjacent side, so it'd be the cosine. So it'd be equal to W2 times the cosine of 40 degrees. And W2Y is equal to W2 times the sine of 40 degrees. And W2 is the square of this plus the square of that, take the square root. So we do have one additional force which I haven't shown it, and that's the force that's normal to the surface. So we have a force here as well that's keeping it from flying into the, just breaking to the surface. So this is, we'll call this the normal force. Okay, so what do we have? Well, let's call this A, call this B. So for A, some of the forces in the Y direction are equal to the mass. I'll call this, well, I guess we'll call it 1, because we'll call this other one 2. So for 1, sum of the forces in the y direction for 1 is M1, A1, and that's equal to, we have two forces. We have T going in positive y direction, and we have the weight going in negative y direction. So that's all we get out of the first one. The second one, we have the sum of the forces in the y direction for body 2, this being the y direction, is M2, A2, and that's equal to, we have the tension T, and in the negative direction we have y, W2y. And you also have the sum of the forces in the x direction. In the x direction, you've got this force pushing down and this one balancing it out. So you have, this is positive, so you have the normal force minus W2x. Now that equals not m times a, but 0 because we don't have any movement in the x direction. Everything's moving parallel to the surface. So it's, in this case, we're moving, so this is the surface parallel, this is perpendicular. We don't have any movement perpendicular. So this really doesn't do us a whole lot. This doesn't give us anything in this particular problem. We will need this when there is friction, but right now we don't need it. So we have these two equations, and what else do we have? Well, the third thing we have is that when this is moving up with positive acceleration, it means this has to go down because it's attached by this cable. And so the positive A here means a negative A there. So what we say is A1 is equal to negative A2. So they're the same magnitude, you just have to worry about the signs. So we have three equations and three unknowns. The unknowns are actually A1 and A2 and the tension. So the unknowns, let's write that down, unknowns are T, A1, and A2. Three unknowns, we have three equations. We know the masses, we know the weights, and we know the weight and the angles. So somehow we have to do some substitution of some sort to get this to work out. So I'm going to substitute in for A1 as negative A2. So the first equation becomes M1, negative M1 A2 is equal to T minus W1. And I can solve for T. So T is equal to negative M1 times A2 plus W2. Okay, and then I can substitute into this one. So I end up with M. So I substitute into another substitution. So what I did is substitute this into there. To get that equation, and then I'm going to substitute in there, so I'll get M2A2 is equal to T, which is negative M1A2 plus W2Y plus, should be W1 right there. Let's fix that. Okay, let's try it again. The tension is going to be substituted in there, which is minus M1A2 plus W1, and then minus W2 sub Y. So I'm going to solve for A2. So we add this to both sides. So those two stay on the left-hand side. Then I factor out A2. A2 times M2 plus M1 is equal to W1 minus W2y. So the acceleration is W1 minus W2y divided by M1 plus M2. And the last thing I need to do is I need to rewrite these in terms of the masses. So we said this, W1 is M1 times G, and W2y is equal to M2 times G times, which one was it? Cosine or sine? Sine of 40 degrees. So we multiply that by the sine of 40 degrees. So now if we plug it all back in, we get A2's W1, which is M1G, minus M2G times the sine of 40 degrees divided by M1 plus M2. So at this point, we can actually plug back in. M1 is 10 kilograms. G is positive 9.8 meters per second squared. 5 kilograms times 9.8 meters per second squared times the sine of 40 degrees divided by the sum of the two, 10 kilograms plus 5 kilograms. So let's see what we get. We get 10 times 9.8 minus 5 times 9.8 times the sine of 40 degrees. That whole thing divided by 10 plus 5. And we get 4.4 meters per second squared. So that's the acceleration. And then if we want to find the tension, we can go back to any one of these equations. So we'll use that one. So the tension is equal to M negative M1, which is 10 kilograms, times A2, which is 4.4 meters per second squared, plus W1. W1 is 10 kilograms times G, which is 9.8 meters per second squared. Okay, so we've got 10 times 9.8 minus 4.4, 54. So I get the tension is 54 newtons. So let's stop and see if that's the right answer or not. Okay, well, I just found out I forgot to push the record button, so I have worked the problem and I'm going to explain it to you. Unfortunately, I've got some steps that, and I did get the right answer, thank goodness. So here's a drawing of what problem 28 represents. We have an inclined plane with a block. There's no friction between the block and the plane. We have a mass that's hanging off of a cable. This pulley is frictionless, so the tension here is going to be the same as the tension there. The mass of the cable is considered to be small, therefore we assume it's 0. So what we do is we look at the sum of the forces for both of these elements, both for element 1 and element 2. So here is the free body diagrams associated with this. So in this case, there's only forces acting in the y direction. We have the tension pulling upward, and we have the weight pulling downward. We define the positive y direction as going this direction, and that's completely arbitrary. I could define it the other way if we get exactly the same correct answers. It has a mass associated with this M1. Let's write that down. So this has a mass M1. And likewise with the second block here, it's going to move parallel to this surface. So there's going to be no movement in this direction, and all the movement is going to be in that direction. If we look at the forces on that block, we have the tension here, which is pulling parallel to the surface. But the weight is not pulling parallel to the surface. It's going straight down. Gravity always pulls it downward. In this case, I've defined X and Y for this body to be different than this. So I have it going Y parallel to the surface and X perpendicular to the surface. There's no movement in the X direction. All the movement's in the Y direction. So what we need to do is we need to take the weight, which is restraining this thing. If there's no weight, it would just fall completely. There'd be nothing to slow this thing down. It would just be a free fall. So you've got this mass and a corresponding weight. So the weight is going down. What we do is we break it into a component that's parallel to the surface and one that's perpendicular to the surface, and they're at a 90-degree angle. Now we know the angle between here and here is 40 degrees. It's this angle right there to there is 40 degrees. And through geometry, we can figure out that this is 40 degrees. What I did was I just thought about if I lowered this thing down so it was going towards more of a horizontal surface, this angle would become smaller. And so which angle would become smaller? When I did that, well, this one would approach a 90-degree angle, so this one would have to approach 0. So if this is approaching 0, then this would approach 0. So these angles have to be the same. So this angle here between the force coming down and the component in the X direction is 40 degrees. So we can just use geometry to find these two forces. W2x, which is this one, is just going to be W2 times the cosine of 40 degrees because it's the adjacent side. It's also going to be, actually it's going to be in the negative X direction, so we should probably put a negative sign there. And as far as this one is concerned, W2y, it's actually in the negative direction also. If we were to, okay. So it's equal to W times the sine because it's the opposite side from the angle, 40 degrees. So those are the components of the weight associated with this angle. So if we look at the forces, some of the forces on element or mass number 1, we know because it's moving, we include the mass of the object times its acceleration. Now we don't know what the sign of this is yet, and it'll work out when we solve for it if we did it correctly. So we have tension going in the positive y direction, it's going up, the weight going in the negative direction, and that's balanced by the mass times the acceleration from the second law. For object number 2, in the y direction, we have the mass times the acceleration into A2. And then we have a tension, which is pulling in the positive y direction, and this weight, which is going in the negative y direction. So it's going to be a negative quantity, so we've got to be careful here. We don't have a double dip here. And in the x direction, which is this direction, we have this force, which is pushing down, and this force, which is pushing up, and they balance each other out. Because there's no movement in this direction, in the x direction, the sum of the forces have to equal 0. In this case, this equation doesn't lend any additional information. We're going to use this one, and we need one more equation. And this just relates the two accelerations, A1 and A2. And the way we do that is we just imagine that this thing is moving in one direction and see what happens with this thing. So if we move up, let's just assume we're moving up, so A1 is positive. What's happening here? Well, this has got to go down. This goes up, that's got to come down because the rope stays the same length. Well, that means that the acceleration, for a positive acceleration here, we have a negative acceleration because it's going to be going in the opposite direction that I defined y. So A1 is equal to negative A2. The magnitudes are the same. The signs are different because of the way we defined our coordinate system. If I defined this the other direction, then they would be equal to each other, both the magnitude and sign. So what we have is so since we have what we have is three equations and three unknowns. Our unknowns are tension, mass, and also tension, and the two accelerations. So that's three equations, and we have three unknowns. So we're able to solve that. So what we're going to do is we're going to do two cases of substitution. So for A1, we can substitute it in here. For A1, we put in negative A2. We solve for T. So T is equal to this minus that, which becomes positive W1. And then we substitute here into this third equation for T. So for T, we put in this. And then we can solve algebraically for A by adding this to both sides. And then we have left W1 minus W2y. Divide both sides by this, we solve for the acceleration. Now we stick the numbers in. Before we do that though, W2y is equal to m2g sine of 40 degrees. So we m2g sine of 40 degrees, m1g, and then we divide by the mass, and we get an acceleration of 4.4 meters per second squared. So that's acceleration, and then we can go back to this equation and solve for t by plugging in the numbers. We get 54 newtons, and those are the correct answers. Okay, this is one of the harder ones. It's a blue problem. It's problem number 34. It's actually called Atwood's machine, and what it consists of is a pulley, and we assume it's a friction. Well, they say it's a frictionless pulley. I'm pretty sure. Yes, it does. And over the pulley, we have a rope, and that rope attaches two masses. So we have one mass going this direction, and we have one mass going that direction. Of course, that's not supposed to be like that. And we have a round mass. Doesn't really matter what the shape is, but so there's a round one just so it matches the book, and we have a square one, which is over here. And basically what happens is both of these masses contribute to the inertia of the system. And the difference in the mass causes this thing to move. If this mass is greater than that mass, then it goes this way. If this mass is greater than that mass, it goes that way. But both of them contribute to the inertia, so the more mass we have, the slower things happen for a given difference in the two. So the difference in weight, difference in masses cause a force difference, which causes things to move. But the force only goes as fast as the inertia will allow us. And so anyway, so let's write down what we know. We know that the mass on the left-hand side is 3 kilograms, and the mass on the second half is 5 kilograms. And it's okay, two objects with masses of 3 kilograms and 5 kilograms are connected by a light string, so there's no weight, that passes over a frictionless pulley. Determine the tension in the string, the acceleration of each object, and the distance each object will move in the first second of motion if both objects start from rest. So the first two parts of the problem we use Newton's second law, and then the third part of the problem we use one of the 4 equations that applies to constant acceleration. So we could actually solve for acceleration or tension and find the other. It doesn't matter which one we do first. Now, because we have two objects, we're going to have two free body diagrams. So let's draw both of them here. So here's the one mass, and here is the other mass over here. And I should move them down just a little bit so there's more space. So what do we have? Well, we have attached to the string, we have what do they call it? Attached to the mass, we have a string. And attached to the other mass, we have a string. So we have a tension here. This one's pulling up. This one's also pulling up. and they're equal to each other. If this was not a frictionless pulley, then they wouldn't be equal to each other. But because they are frictionless, and also there's no mass to, also the pulley has no mass or negligible mass. If we had a mass to the pulley, but no friction, then these still would be equal to each other. Is that true? No, actually they would be different. So it's both because it's frictionless and it's massless. Okay, so those are the tensions from the string. And then we have two weights. We have a weight here, and we have a weight pulling down like that. So let's call this object 1. Call this object 2. So I'm not going to call it T1 and T2 because they're the same thing. But we are going to have two different masses. We're going to have M1. And, well, let's put that as the weight. So that's W1. So this, we'll put the mass up here and the mass there. But the weight pulling down, the weight is always equal to the mass times acceleration due to gravity. And W2 is equal to M2 times G. G being 9.8 meters per second squared. G being positive. Okay, what else do we need to do here? We need to define positive coordinate systems. And we've got two coordinate systems because we have two objects. So just to be different, let's define. Actually, let's do it this way, because if this mass is less than that mass, it's going to move this direction. So we can kind of use our heads here. So let's call this Y, and we'll call this Y. There are different Y's, Y associated with this mass and Y associated with that mass. But in this case, Y positive is going up, whereas Y here is going down. Now I could have chosen it to be up as well. It's completely arbitrary which direction. The only reason I did that is because if this goes up, then that comes down. So positive Y here is positive Y in the second part. Okay, so what do? Well, we use Newton's second law, which says the sum of the forces in the y direction are equal to 0. So for object 1, sum of the forces in the y direction, I don't know if I said 0. If I did, I apologize. But anyway, the sum of the forces in the y direction is equal to m1 times a1. And that has to be equal to the unbalance of forces. So the tension here is going in the positive y direction, so it's positive T minus W1, because this is going opposite. This is going down, this is going up. Okay, there are no forces in the x direction, so we just ignore that. If we look at the second body, the sum of the forces in the y direction are equal to M2 times A2, and in this case we have the tension pulling. In this case it's actually negative because positive y is down, so this is going to be negative T, and then these go in the same direction, so it's going to be plus W2. And then the final one is this connection. We're connected by a string, and therefore the third equation says that A1, in this case, is equal to A2. Now, one of the previous problems, it was negative, and the reason they're equal to each other and there's no sign difference is because if I go up here, if I go positive y on this side, that means I have to be going down on this side, which is also positive y. So in this case, there's no sign difference. And that's one reason I would choose that, so that I don't have a sign issue. Okay, so just like in the previous problem, we substitute this into there, then we solve for the tension from that equation, and we plug that into here, and then the only unknown we'll have is A2. So let's do that. So substitute 3 into there. That means we have M1A instead of A1, we have A2 is equal to T minus W1. Now we solve for T. Now, we're solving for T, but we could have solved for A2, and then we could have substituted. So depending upon what we want to find first, we want to find acceleration first, we solve for T. If we wanted to find T first, we would solve for A and do the substitution. So it's completely arbitrary which one I did. Not arbitrary, because I think they asked for acceleration first, but actually they asked for tension first, but you can see it doesn't really make any difference. So we're going to solve for, we're actually going to solve
three equations for A, and then we'll use that acceleration to calculate t. So when it says solve for t, we take this equation, which was this one with this substitution. Solving for t, you get m1 a2 plus w1. So we just move that to the other side, becomes positive. And now we substitute. We're going to substitute into this equation for t. So we have m2a2 right there is equal to negative t, which is right there, m1 a2 plus w1. And then we have plus w2. Now, what we're going to do is we're going to solve for a2. So that's just algebra. So let's move it. Well, that's the first thing we're going to do is we're going to multiply out this negative. So we're going to distribute the negative sign to both parts of this. And then we'll add this to both sides, which will give us m2a2 plus m1a2 is equal to w2 minus w1. I just switched those. So the positive was first, and negative was second. Then we factor out a2. And we divide both sides by this quantity. So we get a2 is equal to w2 minus w1 divided by m2 plus m1. And finally, before we actually plug the numbers in, we're going to rewrite the weights in terms of the mass and the gravity. So you get the weight for object 2 is the mass of object 2 times g. The weight of object 1 is the mass of object 1 times g. And then we divide by the denominator, which doesn't change. And if we wanted to, we could factor out the g. So a2 is equal to acceleration due to gravity times m2 minus m1 divided by m2 plus m1. Okay, so now we know everything. So let's add a page, plug in the numbers. So there we are. So the acceleration, a2, is acceleration due to gravity, 9.8 meters per second squared. Put that in parentheses. M2 is 5 kilograms. M1 is 3 kilograms. And we divide by 5 kilograms plus 3 kilograms. And before we actually do the calculation, let's just look at what we have. So we have the acceleration due to gravity. If m1 was equal to 0, then these would cancel out, and we just have acceleration due to gravity because there would be nothing holding it up; it would just fall. And the other is true as well. If this were 0, then we'd actually have negative 1 times this, and it has to do with the direction of things falling. Okay, now so if these masses are larger, then the denominator is larger, which means that this is going to be a smaller fraction. So the larger you make these masses in this particular machine, the Atwood machine, the slower it's going to move, the slower it's going to accelerate. Also, this difference times gravity gives you the difference in weights. So the larger the difference in the weights, the faster the thing's going to move, which makes sense. So it all makes sense. So let's plug the numbers in. Got my calculator out of my bag. So there goes my book on the floor, my calculus book. Okay, so 9.8 times 5 minus 3 divided by 5 plus 3, which is 8, gives me 2.45. So let's use red, since everything else is red here. 2.45 meters per second squared. And the units are meters per second squared because the kilograms cancel out. So this thing basically has the weights moving at less than acceleration due to gravity. That makes sense because you have that inertia you got to move and that are connected to each other. So an elevator is kind of like this in that you have the mass of the elevator, and then on the other side of the cable you typically have this big mass as well. And that kind of slows the elevator down, so it doesn't move so fast. Actually, in an elevator, the weights are about the same, and then you use a small motor to get it to move. But anyway, that's the acceleration, and then we can calculate the tension by using either one of these equations. So let's use this equation right here. I'm just going to paste it over. Oops, what happened there? Okay, so we're going to use that equation. So the tension in the cable is going to be M1, which is 3 kilograms, times A2, which is 2.45 meters per second squared, plus the weight, and the weight is just the mass times the gravity, acceleration due to gravity. So we have G, which is 9.8 meters per second squared, and we have the weight, which is, the mass, which is 3 kilograms. So 2.45 plus 9.8, both of those are multiplied by 3 kilograms. So we get 36.8. 36.8 newtons. Kilogram meter per second squared is a newton. So that's the tension. And the third part is the distance each object moves. But before we do that, I'm going to just check the answer before we move on a little bit. Okay, so we're okay. We're good. So the final question is, how far do they move? And they both move the same distance. One moves up and one moves down. In this case, we have to use the kinematics equations. And so what do we know in this case? We know that V0 is 0 because it said it starts from rest, 0 meters per second. We don't know the final velocity. We know the acceleration is equal to 2.45 meters per second squared. And we either need to know the time or the what's left in there, time displacement. Well, that's what we're trying to calculate. The time is the first second, so t is equal to 1. So we know 3 things. Therefore, with knowing 3 things, we can find either one. And so the question was, what is the distance? Delta, we'll call it delta y, is equal to what? So of the 4 equations, I'm not going to, well, let's go write them down. Drill them into your brain. So delta x is equal to v plus v0 over 2, the average velocity times the time. V is equal to v0 plus at. Delta x is equal to v0t plus 1/2 at squared, and v squared is equal to v0 squared plus 2a delta x. That's what I remember. Of course, it's delta y. Well, this is actually the one that's easiest because we have everything. So let's say delta y is equal to v0, which is 0 meters per second, times the time, which is 1 second, plus 1/2 times the acceleration, which is 2.45 meters per second squared, times the time squared, 1 second squared. And so this goes to 0. You can see the units are still meters per second squared. Actually meters per second times seconds. Here we have meters per second squared times second squared, so we get meters. And so we have 0.5 times 2.45 times 1, which is 1.22 meters. Probably round up to 3. 1.23 meters. Okay, so I'm going to stop again, just check the number. Okay, so I've checked the answer and everything's correct. But let's kind of review what we did if you need a review. So I'm going to go back here. If you're okay, just shut it down. So here's our diagram. We have 3 kilogram mass here, 5 kilogram mass here. Frictionless pulley with a massless string. So we don't have to worry about the weights of the string. We draw two free body diagrams, one for the round thing, one for the square thing. We define positive y here as being up and positive y being down here. The only reason I did that is so when I looked at my accelerations later, that there was no difference in signs. This going up means that going down. And so positive A here means positive A here. So they have their masses and they have their weights. We sum the forces in the y direction, which because it's moving is equal to the mass m1 times the acceleration a1. And the force, we have t positive, w1 negative. And likewise with this one we have t negative because y is down, so it's negative t, and w2 is the same direction, so it's positive. And the acceleration is, we don't need to know that at this point. It turns out it is positive because this is greater than that, but if it turned out the other way, we'd actually end up with the acceleration being negative, which would say that it's opposite of what we guessed it to be. The third equation says that the acceleration of this element is the same as the acceleration of that element, and that's because they're connected by the string. So we have the three equations. We substitute for a1 into here, and we get this equation. We solve for t, and then we substitute into this equation for t. When we do that, we get that equation, which only contains one unknown, which is a2. So we go through the algebra, solve for a2, and we get that equation. Then we substitute for the weights. Weight is mass times gravity. Factor out acceleration due to gravity, and we get the final equation. Everything now we know, so we plug it in, 9.8 meters per second squared, 5 and 3 kilograms, we get 2.45 meters per second squared. That's the acceleration. Then we, if we had substituted in here, we had solved for A2 here. If we solved this for A2 and substituted it, then we would have solved for detention. But we just did it that way. Okay, so we plug it back in, solve for the tension, 36.8 newtons. And once we have the acceleration, then we use one-dimensional motion equations to calculate the displacement. And it turns out this is the equation to use because we have v0, which is 0. We have time, which is 1 second. We have the acceleration, which is 2.45 meters per second squared. Plug them in, and you get the answer. So that's how it works. So we're on problem 53, which is a blue problem, which also means it's middle level of difficulty. So let's make a drawing so we have something to deal with. So we have a incline, and I'm going to rotate this around so that it matches in the book. So we have a mass that's going to slide on a flat surface. Well, it's flat, but it's at an angle. So here it is. And then we have another mass that's going to hang downward with no friction. Let's pick that one there so it's longer. And then we have a pulley, which is hanging up here. And we have a cable that connects the pulley with this, and one that goes down like this. So let's just move that over a little bit. And let's call this object 1, this object 2. Object 1 is 7 kilograms. Object 2 is 12 kilograms. So this is going to go this way. If it's going to move, which I think it is moving. And that's because this mass is greater than that mass, so the weight is greater here than that, and being on an inclined plane also it reduces the effective weight, essentially. So let's just find the acceleration reached by each of the two objects shown in figure 453 if the coefficient of friction between the 7 kilogram object and the plane is 0.25. So we're going to, on this page, we're going to do a free body diagram for both masses. So this one's going to be at an angle, and the angle is 37 degrees. So this is also 37 degrees. And we have a tension in the rope. So we have an arrow that's representing the tension. And then we have the weight, which is pushing downward, and that consists of a component that is perpendicular to the plane and one that's parallel to the plane. So we're going to call this W1 because it's mass 1. This is W. Let's define our coordinate system. So since it's going to be moving in this direction, let's define positive X this direction and positive Y this direction. So this is X and this is Y. We'll call this tension T. The pulley is frictionless again, so we don't have, all that's doing is connecting these two in a way that there's no friction involved. Okay, back down here we have W1X and we have W1Y. In addition to the weight and the tension, we have the friction force and the normal force. So the friction force is actually going to be pushing this way because it's wanting to move this way. Friction always goes the opposite direction. So we're going to call that F sub F. F for force, small f for friction. So that's the friction force. And then we're going to have the normal force, which is going to be this direction. So that's our normal force. We'll use F sub N for that, for normal. And this is pushing this way because the weight's pushing down that way. And it turned out those are equal to each other. Okay, so that's all that's happening. A lot of stuff. Tension, the weight, broken into the two components. This angle is 37 degrees. Because as this thing moves, if we move this down towards 0, this angle would become towards 0 as well because this thing would rotate around that way. So that's how I figured out that this angle is 37 degrees. And then we take it the second element, which is this thing. And we have a lot less involved in that. We have a tension pulling up, which is the same as this tension, because the pulley transfers the tension between the two sides. And we have the weight pulling down. So we have a weight. So W2 here. Okay, let's add a page. Now what else do we know? Well, from geometry, we can say that W1X is equal to W1 times what? Well, this is the opposite side from the angle, so it's going to be the sine of, I'm going to just use theta right now, but theta is 37 degrees. W1Y is going to be equal to W1 times cosine of theta. Okay, so now we know these two. We also know that the friction force is equal to the coefficient of friction times the normal force. That's just the relationship between the two kinds of forces and the coefficient of friction. The coefficient of friction is equal to the friction force divided by the normal force. So we can solve for that. What else do we know? Well, let's do the sum of the forces. Oh, let's define positive coordinates here in this direction. So I'm going to choose it to go in this direction. And I could have chosen it to go in the other direction, but I'm choosing positive y here. Positive x is this way, positive y is that way. Okay, so we're going to do the sum of the forces. This is for object 1. Sum of the forces in the x direction. Well, since it's moving, it's equal to m1 times a1. And the forces acting in the x direction, well, in the positive x direction, we have positive t. We have the friction force acting in the negative direction because it's going down, whereas x is going up. And we also have the weight, which is also going in the negative x direction, so W1x. And if you do the sum of the forces in the y direction, we have 0 because there's no movement in the y direction. It's all in the x direction. And what forces do we have? Well, we have in the positive x direction, we have the normal force, and in the negative x direction, we have W1y. So those are our only two forces in the y direction. And then finally, number 2, body number 2, which is here. This is body number 1. We only have forces, some of the forces in the y direction. It's moving in the y direction, so it's equal to m2 times a2. And the two forces we have the tension, which is going up, and we have the weight, which is going down. And the third equation is, well, there's really two equations here. There's actually 4 equations, but the third one we're going to write down here is the sum of the forces. Actually, is the relationship between the accelerations. So if this moves up, which is positive x, this moves down, which is negative y. So there's going to be this negative positive thing. So we're going to say A1 is equal to negative A2. And believe it or not, all these equations we're going to be able to, we also know that W1 is equal to M1 times G. We know that W2 is equal to M2 times G. Now, you'd be tempted to stick numbers in here, but it's not as bad as it seems. So let's start with this one. We know that we can calculate W1y from the geometry. And we'll substitute them for W1y at the end, but so first thing we can say is that the normal force, and I just realized I've got a mistake here, which this should be the friction force here, not the normal force. Okay, so the normal force is equal to W1y from this equation. The friction force is equal to mu times F sub n. Therefore, the friction force is equal to mu times W1y. Okay, now we can substitute that into here. So we'll have M1 A1 is equal to T minus the friction force, which is mu times W1y minus W1x. These two we know, this we know. This we don't know, and then we're going to do the substitution for acceleration. So we can put this in terms of A2. So we have M1 times A2 instead of A1 is equal to T minus mu W1 sub y minus W1 sub x. And if we solve either for A or T, we can plug it into this equation, and the only unknown we'll have either is A2 or T. So let's solve for T, because that's a little easier. T is equal to minus M1A2 plus, because I'm going to change the sign when I move this to the other side, mu times W1y minus or plus W1x. So I'm just moving these two to the other side, and they become positive. So I'm just solving for T, and then I can substitute into here. So when I substitute into this equation, I end up with M2 A2 is equal to T, which is negative M1 A2 plus mu W1y plus W1x minus W2. So here's T. Those three terms are T. And you can look at what we have. We know what M2 is, we know what M1 is, we know what mu is, we know the weights because we know the components of the weight because we have these as well. So I'm going to first solve for A2. So we're going to move this to the left-hand side. So we have M2 plus M1 times A2 is equal to what's left over, mu W1y plus W1x minus W2, and then we solve for A. So A2 is equal to mu W1Y plus W1X minus W2 over M1 plus M2. And then finally, we can substitute in what we know about these other things. So we get A is equal to mu, which we know. W1Y is equal to W1 times the cosine of theta, plus W1X, which is W1 times the sine of theta, minus W2, all divided by M1 plus M2. And then finally, A2 is equal to mu times W1, but W1 is M1 times G. And then we have the cosine of theta plus W1, which is M1 times G times the sine of theta, minus W2, which is M2 W2 up M2G, all divided by M1 plus M2. Okay, so that's the final equation. You could actually do some substitutions earlier if you wanted to. And in this case, it just works out in terms of units better to do it this way. And so let's add one page here and write down what we know. So I'm going back to the problem. Mu is equal to 0.25. M1 is equal to 7.00 kilograms. M2 is equal to 12.0 kilograms. G is equal to 9.8 meters per second squared. And theta is equal to 37 degrees. So that says A2 is equal to mu 0.250 times M1, which is 7 kilograms, times G, which is 9.8 meters per second squared, times the cosine of 37 degrees. And I'm going to have to kind of stagger these. Then we have M1, which is also, again, 7 kilograms, times G, which is 9.8 meters per second squared, times the sine of 37 degrees. Let's put this in parentheses as well. So that's this term, minus M2, which is 12 kilograms, times G, which is 9.8 meters per second squared. And all of that is divided by 7 kilograms plus 12 kilograms. So let's do the calculation. Hopefully I didn't make any mistakes here. And I think it's okay because the first two terms should slow the thing down. Friction should slow it down, and the inertia should slow it down. This is going to be speeding it up because this is what's hanging down, so that makes sense. And this is also the inertia of the two items. So this is actually the forces associated with each item. So it all makes sense. So I'm pretty confident that we're going to get the right answer. 0.25 times 7 times 9.8 times the cosine of 37 degrees plus 7 times 9.8 times the sine of 37 degrees minus 12 times 9.8, which is negative 62.6, divided by the sum of 7 plus 12, and I get negative 3.3 meters per second squared. So that's A2, so A1 is equal to positive 3.3 meters per second squared. And that makes sense too because item 2 was, we defined positive y is going up. So since y was going up, this means it's accelerating downward, which it is, it's falling. And A1 is positive because it's going the same direction. Okay, so that was what we're supposed to find. Let's see what the answer is. Okay. And lo and behold, it is the correct answer. So that's good. So let me kind of explain this again. You don't want to. This is the summary. We draw our sketch. We draw individual free body diagrams for this and for that. We have the tension in the rope wanting to pull it up. We have the friction force wanting to not go as quickly, so that goes down. We have the weight, which goes straight down, but we break that into two components, one that's perpendicular to the surface, one that's parallel to the surface. The one parallel to the surface is wanting to pull it backwards. If I took this weight off, if I cut this, it would just go slide down. So that makes sense. But the friction force is, if the thing is moving this direction, then the friction force, if it's moving this direction, the friction force is pushing opposite the movement, so that's why the friction force is in that direction. And then this unit, you have the tension going up and the weight going down. So we use geometry here to break this weight, which is just the mass times m1 times g, into an x component and a y component. The weights are calculated from the mass times the acceleration due to gravity. You can relate normal force to friction force through this result, or U is equal to the friction force divided by the normal force. So if I solve for the friction force, I get that. Then I use the Newton's laws, perpendicular to parallel to the surface, which is where it's moving. I have mass times acceleration is equal to the tension, positive, friction negative, weight negative. In the y direction, there's no movement, so the sum of the forces equals 0, but we still have two forces. We have the normal force holding it up and the normal weight force pushing down, and they have to be equal so that we don't have any movement in that direction. Then we do the sum of the forces on this element, which is mass times acceleration for this element. Tension is pulling up, weight's pulling down, so that's negative, and the final one is relating the accelerations between the two bodies. And it's the negative sign is here because if we have positive acceleration here, that means it's going up. This would come down. Coming down would be the opposite of our defined direction. So that's where that comes. And you have to go the whole procedure. You have to go through this. The question is, where do I stick numbers in? And let me just put places you could actually stick numbers in. Well, here we could do this. We could calculate these two numbers, because we have the weight and the angles, so that would be numbers, and therefore we could come up with a number here. This part, one of these is an unknown, so we're not going to do that. So we could stick in this number here. This blue number could be here, and then we could also put a number in there. So you can combine these two numbers. So you can combine those two terms as just a number. But we still solve for t, and then we solve for t from this equation, substitute in this equation. So here's solving for t, plugging it in here. You get m2a2 is equal to this term here, minus w2. And then we find out when we've done that, just like previously, we have one unknown, which is the acceleration. There's a lot more terms in this particular case. But we can solve for a2 by putting all the terms that involve acceleration on the left-hand side, factoring out the acceleration, dividing by this quantity. And then when I finally solved this relative to, I had to plug in the corresponding terms for what W1y was, which was W1 cosine theta, W1x is W1 sine theta, and then for weights, I put in M1g, and M2g. And at this point, I have everything that I need, which was given in the original problem, so I just put the numbers in there. Put these numbers in, I did the calculation, I get negative 3.3 meters per second squared, which seemed reasonable because it's less than 9.8. And so that's the answer. And we said A2 is negative, that's because it's falling, whereas the positive y direction is going up, so we know they're opposite directions. Whereas A1 is positive because if we go over here, it's going up, which is positive. So positive direction corresponds with the same direction as the acceleration. So that's how that one works. Not easy, but it just gets a lot of terms. So we finally have a problem. It's not super hard here. It's a black problem. And it's problem number 61. So it's on page 116. A boy coasts down a hill on a sled, reaching a level surface at the bottom with a speed of 7 meters per second. If the coefficient of friction between the sled's runners and the snow is 0.050, and the boy and the sled together weigh 600 newtons, how far does the sled travel on the level surface before coming to rest? So let's draw a picture. So we have it coasting down the hill, and then it hits the level surface like this. And it says that the boy is going 7 meters per second at the bottom of the hill. So right here, our V0 is 7.0 meters per second. And so let's draw our sled here. So he goes along, and then he says it comes to rest. So here we are at some point later. So V is equal to 0.0 meters per second. And let's see, the sled has a mass here, or weight of 600 newtons. And the coefficient of friction is 0.050, which is the ratio of the friction force to the normal force. So we know the normal force is at 600 newtons. So 600 newtons times 0.05 gives us that the friction force is 600 newtons, normal force, times 0.05, and so that's 30 newtons. So that's the force. And there's only one force that's acting in the x direction. So basically what we have is we have a friction force pushing this way, and we have momentum going this way. So there's a mass. So there's a mass associated with this. And let's draw friction force. And so what we have is a mass. Mass is equal to, in this case, weight divided by g, because weight is equal to mass times gravity. So we have weight 600 newtons, and we have acceleration due to gravity of 9.8 meters per second squared. 600 divided by 9.8, 61.2. And so that's 61.2 kilograms. So if we do the sum of the forces in the x direction in this particular case, so the forces in the x direction, since we're moving in the x direction, let's make that positive x. We'll start actually at the left-hand side. So this is positive x. And so it's going to be equal to the mass times the acceleration, and that's equal to, in this case, minus, what is the force? The force is the friction force, 30 newtons. So if we solve for the acceleration, we get negative 30 newtons divided by the mass, which is, did I calculate the mass? Yes, 61.2 kilograms. So we get 30 divided by 61.2, negative 0.49 meters per second squared. So that with the acceleration, then I guess that's it. Well, with the acceleration, then we can do a kinematics problem. So this is a constant acceleration problem. We know that V0 is equal to 7 meters per second. We know that V is 0 meters per second. And we know that the acceleration is equal to negative 0.49 meters per second squared. What we don't know is the time and the distance it takes. So what are they asking us for? How far does the sled travel? So we're trying to find delta x. Which one of the equations do we have that involves v0 va delta x? Well, it's this one. V squared is equal to v0 squared plus 2a delta x. So if we solve for delta x, we'd have v squared minus v0 squared divided by 2a. V squared is 0 meters per second. V0 squared is 7.0 meters per second. And we have 2 times acceleration, which is negative 0.49 meters per second squared. So we have negative 7 times 7, which is 49, divided by 2, divided by negative 0.49, and we get 50. In this case, the units are meters. We get meters squared per second squared divided by meters per second squared, which gives meters. So delta x is 50 meters. So let's just check to see about that. And that's correct. So, how did I come up with this, besides the fact I've done a lot of these problems? Well, I started with the drawing, and I kind of tried to put everything that I knew on the drawing, and then put the equations that might apply, and then it kind of just came to me that, I knew the force as far as the restraining force. And I thought, well, are there any other forces besides the friction force that are in the x direction? Well, no, because nobody's pushing it. The only thing it's doing is it's being pushed to slow down. And so I knew that was the force, and I knew that Newton's second law related force, mass, and acceleration. Then I said, okay, do I know the mass of this object? Well, I know the weight, so I can back calculate the mass. So knowing the force and the mass, I should be able to calculate the acceleration. And once I knew the acceleration, and I assumed it to be constant, in this case, I don't even have to assume it is constant. I know it's constant. Then I said, okay, how do I predict distance knowing acceleration? And I said, okay, well, that's chapter 2 stuff. Saw what I had. Saw that I had the initial velocity, the final velocity, and acceleration. That allowed me to calculate the time and the delta x. So I picked the appropriate equation to do that and got the right answer. So we're on problem 62 now. And I'm just trying to get my tablet to show my pen. Oh, there it is. So problem 62 says a 4 kilogram block is pushed along the ceiling with a constant applied force of 85 newtons acting at an angle of 55 degrees into the horizontal. So let's draw a horizontal line. Let's draw a block. And now we have a force which is 85 newtons acting at an angle of 55 degrees with respect to the horizontal. So here it is. So the angle with respect to the horizontal is this angle. So it's 55 degrees. We'll call this F. And it's going to have 2 components. It's going to have a X and Y component. So let's put those in there. 1, 2. Okay, so we'll call this F sub X. We'll call this F sub Y. We'll have a friction force, which is pushing out here. We'll call this F sub F, small f sub F, which is the friction force. And let's see, determine the coefficient of friction. So we don't know what that is. Let's see, what is the mass of the block? So the mass is equal to 4.00 kilograms. So we'll have a weight associated with this, which will be pointing downward. And let's define our coordinate system. let's define this as positive x, this is positive y. So, what do we know? We also have, let's see, we have a normal force acting here. So this is our normal force that's on the ceiling that's pushing down. So we have the weight, this force pushing up, and the normal force. And this has got to be greater than that so that we have something pushing up against the ceiling. Otherwise, there would be nothing to hold it up against the ceiling. So let's look at the sum of the forces. Sum of the forces in the y direction. What's the acceleration in the y direction? 0, because it's a solid ceiling. So there is no movement in the y direction. So that's equal to 0. And what do we have? We have the weight, which I forgot to write down there. So we have the weight, which is in the negative y direction. We have F sub y, which is in the positive y direction, this component. And then we have the normal force. Then we have some of the forces in the x. Well, it can move in the x direction. So we have mass times acceleration, and the forces in the x direction. We have this one, which is pushing it. So we have positive F sub x because it's pushing the positive x direction. And we have the friction force, which is pushing in the negative x direction. And we have the relationship between coefficient of friction and the two friction forces. Well, not the two friction forces, but the friction force and the normal force. And I think that's enough equations with unknowns, but we can check that out. Oh, we also know that F sub x is equal to F times either the cosine or the sine. Here's the angle, so that's the adjacent side, so it's going to be the cosine of 55 degrees, and F sub y is F times the sine of 55 degrees. So let's just check this again. No movement in the y direction. The weight is in the negative y. F sub y and F sub, oh, actually F sub n is in the negative direction, so that should be negative. F sub y is pushing up. Okay, so then in the x direction, we have mass times acceleration, F sub x, which is in the positive x direction, and the friction force, which is in the negative x direction. So that looks pretty good. So we're seeing if we know everything now. Well, we could plug these in and we'd have just F, so that would be on one unknown. We have F sub n and F sub f, so we have three unknowns and basically three equations. So we can solve for the unknowns. So probably the thing that makes sense is to find these forces and then plug them in to find the coefficient of friction, I think. So, do we know the force? Okay, yes, we do know force. The force is 85.0 newtons. So let's solve for the normal force. The normal force is going to be equal to negative W plus F sub y. And that's equal to minus W is the mass times acceleration due to gravity. F sub y is equal to F times the cosine of, of the sine times the sine of 55 degrees. So I think we know everything there, so let's do this. Negative m, mass is 4 kilograms, acceleration due to gravity is 9.80 meters per second squared. Plus F, which is 85 newtons, times sine of 55 degrees. So let's see what we have. Negative 4 times 9.8 plus 85 times the sine of 55 degrees. So the normal force is equal to 30.4 meters of newtons. Okay, what else do we know? The block accelerates at 6.0 meters per second, so we know A is also 6.00 meters per second squared. So now we can go to the second equation, which is up here somewhere or down here somewhere. Here it is, this one right here. And we can solve for F sub F. So F sub F is equal to the mass times the acceleration. Actually, it's going to be minus. If we add this to both sides and subtract this from both sides, we'll end up with F sub x minus mass times acceleration. So F sub x is F times the cosine of theta, cosine of 55 degrees. Then we subtract mass times acceleration. So the friction force is the force, 85.0 newtons times the cosine of 55 degrees minus the mass, which is 4.00 kilograms. Times acceleration, which is positive 6.00 meters per second squared, accelerating because we're increasing the velocity in that direction. So the friction force is 85 times cosine of 55 minus 4 times 6, which is 24.8 newtons. So the coefficient of friction is just the ratio of the friction force to the normal force, which we now have both of those. The normal force is 30.4 newtons. The friction force is 24.8 newtons. And we take that quotient, we get 0.81, 0.81. So let's pause for just a second, and we're going to check to see whether we're... Okay, so I've checked the answer, and they had one additional significant figure, which I wondered about because I've been carrying 3 significant figures. So the additional significant figure that I got was 4. Otherwise, we're good.